Good morning, Cisco Cohort 2. It's just after 9 o'clock, and it's time to get going with today's Death by PowerPoint presentation on modules 4 and 5. Today we're going to be talking about the physical layer. This is the layer that we have. The three big things that are happening are what kind of bit represents a 1, what kind of electricity represents a 1 or a 0, how fast are the 1s and 0s being transmitted, and how do we physically get these bits transmitted along some medium, like a fiber optic cable or a twisted copper pair cable or something of that nature. We're also going to look briefly at number systems, because in networking we have our binary number system. Computers are binary devices, and we have to some means of representing these binary values. We'll be looking at the binary number system so that we can do the dreaded, feared, and hated subnetting later on. And then we'll also look at the hexadecimal number system, which is widely used for representing very, very, very large numbers like 48-bit MAC addresses and 128-bit IP version as 6 addresses. Okay, let's see. I'm going to go ahead and start sharing the first presentation. Should be this one. So, Module 4, physical layer. And let's talk about what we're going to be talking about in here is going to be purpose of the physical layer. What its purpose and functions. What are some of the characteristics of the physical layer? Then we'll look at some types of media. We're going to look at copper cabling. We used to use the old coaxial cable. Now we mostly use twisted pair cable. We'll look at unshielded twisted pair cabling, which is overwhelmingly what the choice of the cable that we use for very low cost and yet pretty high speed, gigabit Ethernet and above, pretty easily done with cheap old unshielded twisted pair cable. Good for about 328 feet or so. Then we'll look at fiber optic cabling. If we need super speeds or longer distances, fiber optic cabling, it's more expensive, it's more difficult to hook up and put the connectors on it. But if you need to run between two buildings in a campus environment and it's more than 328 feet, fiber optic cabling is a good choice for that. And it usually, fiber optic cabling is usually capable of higher speeds, higher bandwidths. So while you may be able to get 1 gigabit on a twisted pair copper cable, you may be able to get 10 gigabits or 25 gigabits or 40 gigabits or 100 gigabits or even higher on fiber optic cabling. And then we'll look at wireless media like Wi-Fi, connecting things together without having to actually plug cables together. So let's look at the purpose of the physical cable. We have to have some sort of physical connection to a local area network. At home with your router, you have the 4 RJ45 Ethernet cables on the back of your home router that you can plug things into. And then you have your Wi-Fi circuit built in where you can physically send radio frequency energy back and forth to make a connection to a wireless type device. So wired or wireless. A network interface card is a physical device that, for example, on a desktop PC, you can plug in a network interface card onto the PCI socket on the inside of the device, take the cover off, put it in, and it has an RJ45 connector, and you can plug an Ethernet cable into that, and you can connect that desktop PC to the network. Some devices have built-in network interface cards, Roku, television adapters, Game Boys, things of this nature, might have an RJ45 connector built right into them to connect the device physically to the wired network. Most devices just have one network interface card. So a desktop PC usually just has one NIC card. Some devices may have multiple network interface adapters, Ethernet adapters. So a Cisco switch has got 26 wired Ethernet connections because it's a hub that you can plug a bunch of devices into. The desktop PCs that we use in the student lab have 3 Ethernet connections in them. They have one connection, the one that came with the device that's in the motherboard, connects to the Tarrant County College physical network so that we can get internet connectivity for all the PCs and all the labs. And then we have 2 extra NIC cards that are connected to the PC, so you can have a PCA and a PCB on your virtual VMware virtual machines, so we can do Cisco labs in there. Not all of these have the same level of performance. So the Dell computers that we have a very fast gigabit Ethernet connection on the motherboard. There is a second PCI card that's plugged into those machines that is also gigabit performance. But the third NIC card that's plugged into those computers is a USB attached adapter that plugs into one of the USB ports on the back panel, and it only goes to fast Ethernet speed, 100 megabit Ethernet speed. So it's not quite the high level performance as a plug-in card. So looking at the physical layer, this job is to send bits across some type of network media, which could be copper cable, fiber optic, could be Wi-Fi, radio frequency energy. So what we're going to do is each host machine is going to take some upper layer data. It's going to take that user data and maybe encapsulate it in a TCP segment, could be a UTP segment. He'll take that segment, he'll number it, he'll put it in a network packet, IP packet. That IP packet will be encapsulated into an Ethernet frame, and then the data that makes up the Ethernet frame, the binary data that makes up the Ethernet frame, the ones and zeros, will then be transmitted through the local media, through some sort of electricity where some sort of bit of electricity, some sort of electricity represents a 1, some other sort of electricity represents a 0. Through a fiber optic cable, it might be a flash of light means a 1, and a no flash of light means a 0. And in radio frequency energy, we'll use the radio frequency encoding to represent the 1s and the 0s. Once that data proceeds from one host machine to another host machine, that receiving host machine will receive the bits, he'll put them together. He'll use a little mechanism we haven't gotten to yet. We'll do this next week when we look at Ethernet frames. The bits will be assembled into an Ethernet frame, and then Ethernet has a mechanism for checking the frame to make sure that it doesn't have any errors in it. And if it has any errors, he's just going to discard the frame, and we'll retransmit the data. But if the frame is found to be without error, he will go ahead and open up the Ethernet frame. The receiving host machine will go ahead and open up the Ethernet frame and pull out the network packet, and the network packet will be opened up. He'll pull out the TCP segment. The TCP segment will be opened up. He'll send out that chunk of data to, in this case, it's a web server and a web browser. So you'll start to build up that image in your web browsing software that you're using on your PC, like Microsoft Edge or Internet Explorer or Mozilla Firefox or Google Chrome or whatever web browser you're using. You'll be able to see what that graphic designer that created that web page, that author intended you to be able to see. Now here's some physical layer things we need to worry about. So here's our dreaded, feared, and hated OSI 7-layer reference model, and most of it is software. Now here, okay, Hicks rule of engineers. This is the Hicks rule of engineers. You can count on this. The only thing that 2 engineers can agree upon is that the 3rd engineer is wrong. So when all these people sat around the table and came up with the OSI 7-layer reference model, and they said, well, it's going to be 7 layers. And then some other engineers at the IEEE says, you numbskulls, that data link layer is half software and half hardware, and it should have been an 8-layer model. So in other words, when you go and buy an Ethernet adapter from, well, you can't buy it from Prize anymore, I guess. Go and order a Ethernet adapter, either a USB type that plugs into the back of your box so you don't have to open it up, or you can get a PCI adapter card, option card, and put it inside your PC. It'll plug in. You have to take the cover off and put it in and close the cover back. And there's 2 things that come in that box. In that box with that Ethernet adapter is an actual something with a printed circuit board in it that you plug into your computer. That's the physical part of it. And then there's a driver disk that has the device driver. In Windows, the device drivers are the lines of code, the software lines of code that shim and attach and adapt that physical device so it can go connect and communicate with the Windows operating system. So the Internet Engineering Task Force, these are the TCP IP standards that are in software. They're lines of code in the Windows operating system, or they're lines of code in the Linux or the Mac OS X operating system, whatever operating system you happen to be running on your device, the Chrome operating system, if you have a Chromebook. The Internet Engineering Task Force are the group of volunteers that made up all these open standards that what the Internet is today. The Internet runs on standard TCP IP code. Then the physical layer standards are implemented in hardware. This is actual stuff that actually costs money. We have to, mine tin and make printed circuit boards and put components on them and solder components onto the printed circuit boards and come up with a network interface adapter or something of that nature that actually costs money because it has physical parts that we have to put together. So there's many organizations that control this. such as the Internet ISO organization. That's the same international organization that, well, if you're talking about making automotive parts, for example, we have metric and we have SAE standards. The ISO says, well, how many threads per inch is there in a number 8 screw and a number 8 bolt? Then the EIA, TIA, the Electronic Industry Association and Telecommunication Industry Association are trade groups, vendor trade groups that represent the interest of the manufacturers and vendors of these devices. And it's in their best interest to sell a lot of stuff. So they have found that if they standardize stuff, they can get more sales. As an example of this, the RJ45 connector. That's that Ethernet connection that you find on the back of your PC. That same RJ45 socket that you find on patch panels. That's a standardized thing that everybody standardized on. All buildings in the world have been wired with RJ45 panels, patch panels, and circuits over the past 30 or 40 years. And any type of network connectivity you need will fit on that RJ45 connector. The International Telecommunication Union used to be the CCITT. This is the International Organization of Telephone Companies, so that you can make a telephone call from one company which uses one type of standard for its telephone calls to another one. But most importantly, when you make a long distance call, the billing gets worked out and a proper person receives a long distance bill. The American National Standards Institute is similar to the ISO. They have standards for things like how many threads per inch on bolts, but also electrical standards. And then finally, we have our International Electrical Engineer Society, which are the ones that said, oh, you ISO guys that came up with a 7-layer model, oh no, it should be 8 layers. I'd like to compare the 7-layer ISO reference model to, we have the ISO model, which has 7 layers, and we have the TCP/IP model, which only has 4 layers. And I said before, all models are faulty, some are useful. So the ISO layer is useful for learning and teaching, networking. We can zoom in on one particular thing. Today, we're going to zoom in on the physical layer and just talk about aspects of the physical layer. What's a 1 bit? What's a 0 bit? I like to compare this to the city of Fort Worth has got a building code, and it's got lots of stuff in there. For example, if you live in Westover Hills, you might have a tennis court and an elevator, because these are like mansions. So there are lines in the building codes for Fort Worth about, how can you build an elevator that meets the building code? How can you build a tennis court in your backyard that meets the building code? It's got to be, so many feet away from the fence. Does that mean that because the lines that are in the building code that all houses must have elevators and all houses must have tennis courts? No, it doesn't mean that at all. So the OSI 7-layer model is like tennis courts and elevators. They're so complex to it. The TCP/IP code is more like, well, here you've got a house in the Southwest Arlington here, and it doesn't have a swimming pool, it doesn't have a tennis court, it doesn't have an elevator. It's just a regular old 3 or 4 bedroom house. So that's why the OSI 7-layer model looks more complex. It was put together by a bunch of academics and engineers that sat around a table, and everyone had to feel that each participant was satisfied that something he put out is put in the code. And that's why it turned into a complex model. Okay, let's go to the physical layer and talk about physical components and this concept of encoding and signaling, representing our bits, our ones and zeros. So the physical components are, these are the actual hardware that actually costs money that transmits the signals. So a hardware device on my desktop PC might be the Ethernet card that plugs into the motherboard, or most motherboards, computer motherboards these days actually have an Ethernet circuit that's completely on the motherboard. You don't have to plug in an option card. Then the media is maybe a twisted pair of copper cable with an RJ45 plug on it that plugs into that motherboard and carries that circuit over to your home router and plugs in. Or it could be wireless media. It could be a wireless Wi-Fi circuit with an antenna, and it transmits radio frequency energy, and that radio frequency energy is the media that travels through the air and connects to your home router so you can get connection to the internet. So these are all considered physical layer things. Now let's look at this encoding scheme. We know that from our computers, I like to call this the Computers for Terrified Adults class, our Computer Fundamentals class, which is checking up the basics. Computer's got a CPU and RAM and ROM, and it works with bits and bytes. So eventually everything inside a computer is stored in the form of ones and zeros, bit levels. We take 8 bits and put them together, and we get a byte, and that can represent a character for the alphabet, or a numeric value, or an instructional code, a machine language code for a CPU to execute. So what we want to do is take these zeros and ones. We took this upper layer encapsulated data, and we took the data and we put it in a segment. We took the segment and we put it in a packet, took the packet, put it in an Ethernet frame. The Ethernet frame has now been created by the Ethernet adapter, and he needs to send the bits representing this upper layer data, this encapsulated encoded data, out over the media, probably a twisted pair of copper cable with an RJ45 on it. So encoding converts the stream of bits into something that can go on the wire. So in this example, this chart shows this purple line. This is the electrical voltages representing ones and zeros. And this is a method called the Manchester encoding, which was used by the original Ethernet circuits of 40 years ago. And it uses any transition that goes from a high voltage to low voltage is considered a bit, 0 bit. And any voltage that goes from a low voltage level to a high voltage level is considered a 1 bit. So in this case of this purple line, it represents the bit pattern 0, 1, 0, 0, 1, 1, 0. And the original Ethernet was very slow. It was only about 10 megabit. But now we're transmitting, typically 1 gigabit Ethernet over the same twisted pair cable that used to carry the old 10 megabit Ethernet. So they use different encoding methods so they can get faster streams. Ethernet has gone from 10 megabit to 100 megabit to 1 gigabit to 10 gigabit and then higher and higher multiples of that. So each of these methods, speedier, faster methods, uses a different encoding scheme to get this over that same sloppy, crummy copper cable from one point to another point. So if we have signaling, these bit values, how are they represented on the physical media? It's going to depend based upon the type of media that's being used. If it's copper cable, we're going to send some sort of voltages over a copper cable. So let me see, activate the pencil. So this one down here, electrical signals over copper cable. Now in the previous scheme, we just had two levels. We had a high and a low, and the transition from the high to low represents a 0, and the transition from low to high represented a 1. But you can't get very quick with that over standard copper cable. So to get something like gigabit Ethernet speeds, we have to have not just 2 voltage levels, we have to have like 16 different voltage levels. So this purple thing that looks like a city skyline is all these different voltage levels, so that instead of just having a high to low or low to high, we can have transitions from 16 different voltage levels, and we can put a lot more bits into the same amount of time over a standard copper cable. Now, fiber optic cable, we're going to use pulses of light. And we're going to send maybe we'll turn the light on, and that's a 1. We'll turn the light off, that represents a 0. Or with more modern fiber optic technologies, they actually use different colors of fiber optic light. And they can use this to transmit much higher rates of data over the same fiber optic cable. Now, over a wireless, we're going to use some type of radio frequency energy. And we're going to use take our digital signal, and we're going to convert that digital ones and zeros into some sort of voltage that goes through a radio antenna and creates a radio frequency energy that goes into the air. Bandwidth, how fast can media carry data? So when you get an internet circuit from your internet service provider, you purchase a certain amount of bandwidth. So most of you guys are on cable, aren't you? So the cable companies are now advertising, what, 200, 300 megabit, and maybe a gigabit if you have fiber optic cable. I'm still on the phone company. I was on the old DSL until a couple of years ago, and it was 5 megabit. That was pretty slow. It was pretty fast back in the 90s. That was 3 T1 circuits. Today, that's considered very slow. But my DSL broke, and like most of the phone companies in the United States, they're not repairing their circuits anymore. They're forcing you to go to a different type of technology, and I went to a new super high, very high bit rate DSL. It's about 80 megabit. So I'm not as fast as you cable guys, but it's plenty fast enough to watch, several streaming TV shows at the same time and download data pretty quickly. So digital bandwidth is the amount of data that can flow from one place to another. How many bits can be transmitted in a second? Like 80 megabit per second is what I get from the telephone company. So this is going to determine what type of media you're using. And if I wanted to get much faster service, I could get they've been in our neighborhood pushing pipe. You guys know what that means? They're pushing pipes through the ground that they can feed fiber optic cables through, so that they can offer the people in the neighborhood fiber optic gigabit service and charge them a little bit more money for it. So these units of bandwidth depend on how fast that you can put the data through there. Now, latency or delay, it takes a certain amount of time for electricity through a copper cable, which flows pretty fast, about 2/3 of the speed of light, or light pulses through a fiber optic cable, which actually travel at the speed of light since they are light. It takes a certain amount of time for the bits, the encoding, the signaling that represents the ones and zeros to travel across that fiber optic cable or that copper cable. And then they have to pass through intermediary devices that make the path determination decisions on the way, like your home router, your ISP's router that you connect to. There's usually about 10 routers between you and whatever website you go to. And all this introduces a small amount of delay. A very small amount of delay, you hardly measure, you won't notice the delay, but that's what we call latency. So if we have too much latency and too little bandwidth, you get the scrolling circular screen of circus pinwheel of death when you go into the YouTube and you can't watch your video, it won't go at the right speed. Now, throughput, the measure of the transfer of bits across the media over a given period of time. Similar to bandwidth, we're going to measure the bits and see how much we get in a minute or an hour. Now, there is some necessary overhead for all these protocols. Each one of these protocols that encode the data, de-encapsulate and encapsulate the data, add a little bit of overhead. And as a rough rule of thumb, if my bandwidth is 80 megabit, how fast can I download a file? Well, let's see. If it's 80 megabit and there's 8 bits per byte, I should be able to download 10 megabits of data continuously. But I don't get quite that much because there's a little bit of overhead with encapsulating and de-encapsulating the data. The TCP, positive acknowledgement and retransmission, checks for all the data being received properly. It adds a little bit of overhead. So as a rough rule of thumb, subtract about 10% to 20%. So my 80 gigabit of data, maybe I'll get about 8 megabytes of data. 80 megabytes, not 80 gigabytes. I don't got 80 gigabytes. I got 80 megabytes. If I had 80 gigabytes, that would be great. So this is the good put. This is the throughput or the bandwidth minus the traffic overhead. All that necessary protocol overhead that makes everything work properly. Now let's talk about copper cabling. Very common type of cabling, mainly because it's very inexpensive. It's easy to install. Now, in the old days of the Cisco Networking Academy, the Cisco Network Academy has been around for over 20 years now. I've been teaching Cisco Academy for over 20 years. And we used to make you make cables. You'd make cables and crimp cables, and it was pretty easy to take a length of wire and cut off the insulation and strip the wires back and crimp an RJ45 connector onto it. These days, with the advent of, oh, I can go to Monoprice and for 47 cents I can get an Ethernet cable. So I'm not going to make Ethernet cables anymore. So we don't make you guys make Ethernet cables anymore. Just plug things together and configure the Cisco devices. So it's very low cost cable, fairly easy to install compared to fiber optic cable. Yeah, twisted pair copper is easy to install. Fiber optic cable is very difficult to install properly. Not something I can teach you in an hour. Low resistance to electrical current flow. Oh, let's go back to 8th grade physics class and electricity. So in electricity, we have current and voltage and resistance. And wires have a certain resistance or opposition to the flow of current through them. And that's one of the reasons why the copper cables can't be longer than about 328 feet. If they get much longer than that, they have too much electrical resistance. And that high current of electricity that was a 1 is now, as we say in East Texas, it's petered out too much. And now it looks like a 0. And so we have an error in our data. So the limitations are the attenuation is as the diminution or petering out of the electricity representing the 1s and 0s as they go through a much longer length of wire. Also, there's outside interference sources. In our classroom, they just replaced all the overhead lighting fixtures. Instead of the old 277 volt fluorescent lighting fixtures with ballasts that emitted a bunch of electromagnetic interference. And they replaced these with LED panels that operate off of it. They don't have transformers, don't emit radio frequency, they don't emanate electromagnetic interference. Radio frequency interference is the interference you might get from like across the street from the college. There's a big radio tower that's the Tarrant County Fire and Public Safety radio transmissions to all their cars and trucks. So if you're close to something that has radio frequency energy, that can produce interference and corrupt the data. Crosstalk is the next time you're in the lab, look at all the wires that go from all the computers back up to the panel, the Cisco racks in the back of the room, and you'll see they're all bundled together very tightly. You got 50 wires strapped together very tightly with tie wraps. Anytime you have an electrical current flowing through one wire and there's another wire next to it, it will induce a small amount of undesired electrical current in that second wire. That's called crosstalk. So we want to try to eliminate this stuff. We do that by twisting the wires together. And if it's really a noisy environment, we'll put shielding on them. So we're going to mitigate these faults. We're going to only allow the cable lengths to be within a certain length. So in most commercial buildings, you'll find a wiring closet somewhere and put your Ethernet hubs, your Ethernet switches in there. And it's usually less than 300 feet between that room and all of the offices and cubes and everywhere that we need to connect a device to the company network. If you're in an environment where there's a very noisy environment, now in most commercial office buildings, unshielded twisted pair cable will work just fine. Just the twisting together the cables is good enough. But if you're like at a auto manufacturing plant and there's a welding machine going on right next to you, and the welding machine is generating all these big sparks, we might need to use a shielded cable because the unshielded twisted pair cable can't handle that. So we can shield, just like you guys know about PA systems, guitar amplifiers, all these wires that connect the guitars and the microphones and bands together, they have to be shielded, otherwise they pick up a bunch of hum. Okay, so here on the upper left-hand corner is regular old unshielded twisted pair cable. This is what 98% of the time, this is what we're going to use when we wire up any type of Ethernet network anywhere. Just the twisting together of the wires is good enough to cancel out. It's called the self-cancellation effect. It cancels out any outside noise, because any noise like crosstalk or electromagnetic interference that hits that wire, well, since the wires are twisted together, they're going to kind of phase each other out and reduce that effect. If it's next to a super welding, big high current super welding machine in a factory, we might use a shielded twisted pair cable, which shields, puts a copper shield, a foil shield around the entire wire, like you would have to do with a microphone cable or a guitar cable, or you get excessive hum in your audio signal. The shielded twisted pair cables are a little bit more expensive, more difficult to terminate, and the RJ45 connectors and patch panels are a little bit more expensive because they have to have the shielding extra connecting for there. And so if it's a really high noise environment, though, we have to use that. Now that thing at the bottom, it looks like a cable TV coax. Coaxial cable has a single wire in the middle and a shield around it, so it's already shielded. This is what was used in the early days of Ethernet networking. They used big, thick coaxial cables to connect all the devices together. And the coaxial cable is very rigid, it's difficult to bend. We had to connect taps to it to connect to all the PCs. So this is not very commonly used anymore. Coaxial cable has been pretty much replaced because the telephone guys got in touch with the networking guys around the late 80s and says, you're nuts to use these coaxial cables. Why don't you do like we phone guys have been doing for 100 years and use cheap twisted pair cable? The twisted pair will take care of all your noise just fine. Try it, you'll like it. And overwhelmingly about 1990, we pretty much switched to twisted pair cable. So unshielded twisted pair cable is the most common type of media. We're going to put an RJ45 connector on each end of this wire, and then that RJ45 connector will plug into the desktop PC's Ethernet adapter, or the little plug in the wall where you plug in your office, and then back in the network closet where the network switches are located, Ethernet switches located, we'll patch all those together and plug them in. So the outer jacket, this number 1 on the diagram, is this is a plastic jacket. It protects the inside wires from being bent or damaged. Fire code thing. There's a couple types of jackets. PVC, polyvinyl chloride jackets, are the cheaper ones. However, if you're in a commercial building or a business building, most fire codes require you not to use PVC because if there's a fire in the building, and when PVC burns, it emits poisonous gases, and then those gases get sucked into the air conditioning system and they poison everybody that's occupying the building. So most of these areas require what's called plenum rated cable, which is a type of covering that will not emit poisonous gases when it burns, and it triples the cost of the cable, but we have to use it in a commercial building. The number 2 are the twisted pairs. So as these pairs are twisted together, any interference that is received from the outside world, is my pencil still on? Here's some interference coming from the outside world, and it hits this wire at this point, it's this wire at this point, it's this wire at this point. And because they're twisted, they're kind of all out of phase with each other. And if I have 2 signals and they're out of phase with each other, they cancel out. So that means that reduces the electrical interference. There's a specific color code on all of these 8 wires so that when the technicians, the wiring guys, take these connectors, when these are punched down on RJ45 connectors, the wiring that goes hidden in the walls of the building, it's a standard color code. It's all wired exactly the same way. We want pin 1 of the jack to be equal to pin 1 on the other side of the jack. Shielded twisted pair is electrically, it does the same job as unshielded twisted pair. It conveys the 4 wire pairs, the bit levels in them, but it adds some extra shielding to each individual wire pair, and then a master shield around the entire enclosure. So it has much better noise protection. Shielded twisted pair cable is better than unshielded twisted pair cable. It's more expensive, it's harder to install. We have to use special RJ45 connectors that have a shield around them and have a 9th wire to connect that shielding to it. So in a very high noise electrical environment, like that welding machine at aircraft defense plant, you might need to use shielded twisted pair cable. Okay, sorry, I had muted the microphone. Okay, I'm back. So, unshielded twisted pair cable has four pair of wires. No shielding is used. So the self-cancellation effect means I'm going to twist two wire pairs together, and category 5, category 6, category 7 cable, the higher the number, the better made the cable is, the more tightly twisted together the wires are. And so this twisting together self-cancellation effect cancels out outside interference. Kind of in phase, out of phase, cancels each other out. And they are twisted together slightly differently so that the four wire pairs here don't actually interfere with each other. We have to worry enough about them interfering with other cables. Okay, unshielded twisted pair standards and connectors. The old category 3 cable. So back in the early 90s, when all we had was standard 10 megabit Ethernet, we would use category 3 cable because it was good for about 10 megabit. At the time, there was also another competing networking standard called token ring. It was 4 megabit per second. So category 3 cable was fine for that. So I'll tell you a story. I was working downtown at Harcourt Race College Publishing. I worked there in the 90s as a network engineer. The old Novell networking, I'm really dating myself. And they had come and wired the entire, we leased about 80,000 square feet in the City Center 2 building, downtown Fort Worth. And it was all been completely wired with category 3 cable, just when I came there, about 1991. And so we were running standard 10 megabit Ethernet, which was the standard of the time. Now, in about 1995, fast Ethernet came onto the market, and everyone said, oh, we got to upgrade our networks to fast Ethernet. Well, guess what? Fast Ethernet doesn't run real good on category 3 cable. It needs category 5 cable. So I said, well, we just have to replace all our category 3 wiring with category 5 wiring. And upper management said, oh, no, that's too expensive. We're not going to do that now. They didn't do that until later on. So category 5 cable is twisted together and made better. Category 6 cable is twisted together even tighter and has even more bandwidth. So category 5 cable was good for, it was supposed to be good for 100 megabit Ethernet, but actually you can run gigabit Ethernet over just fine if the distance is not too long. So in our classroom, laboratory classroom at the South Campus, we have category 5 cable connecting us back to the wiring closet, which is right outside the door of the classroom. It's only 30 or 40 feet, and we can run gigabit Ethernet over that just fine. But if you were doing an installation today, brand new, you would probably want to use category 6 or category 7 cable for this. And in a commercial environment, you probably will get to do the new installation because the trend now is if you're a tenant of an office building where you're leasing office space and you leave, they rip everything out. So when the new tenant comes in, he has to hire a building contractor, a cable contractor to come in and I'll run all new cable. The RJ45 connector is what's used for connecting to the end of category 3, category 5, category 6 cables. This is the standardized connector. Remember the EIA 568A standard specifies this standardized connector to use everywhere throughout the world for computer networking purposes. And the connector is the male end that's on the end of a wire. And the socket end is the one that's in like the receptacle of a desktop computer where you plug in the Ethernet connection, or the keystone jacks that we put in the wall to plug your computer to the wall connection in your office together. Now, on the right-hand side, we have a properly terminated unshielded twisted pair cable that looks really nice and pretty. Excuse me. And then we have a poorly terminated cable. The category 5 cable actually has a specification that says you cannot unravel the wires more than 1/2 of an inch. And it's kind of actually difficult to only strip the wire back, only strip the cable jacket back only 1/2 of an inch and line those wires up with the proper slot of the 8 slots in the cable where you put it in and crimp it. So the poorly terminated one here that looks like about 1.5 inches. So that's not twisted together properly. That could pick up interference. So that's why they have the specification that says only untwist the bare minimum amount you need to properly put it in the connector and crimp it. So Thankfully, now you are relieved of the onerous duty and obligation of having to strip cables and put the wires in and crimp them on and test them and make sure they work properly, because you can buy them so inexpensively now. Now, we talked about, I think I briefly mentioned the 3 cable types in Cisco. The 2 that are listed here are straight through and crossover cables. In a straight through cable, the pin 1 of the first end of the wire goes to pin 1 of the second end of the wire. This is a Ethernet straight through cable. Both ends have to be the same wiring standard. Now, I didn't mention this yet. The EIATA 568 standard, there's 2 standards, A and B. And they're different color codes. So if you buy a patch panel, you can buy an A or a B patch panel. It doesn't matter which one you use, just as long as you use the same A throughout your company or the same B standard throughout your company. So that means if I buy a 568A patch panel, all my wall jack and keystones have to also be type A. If I buy a cable, it has to be type A or type B at both ends. Just as long as each individual wire is the same on both ends, it's a straight through cable. A crossover cable is what we used to have to use to connect 2 similar devices together. Like if you bought a second PC and you wanted to back up your old PC to your new PC, right click and share the files and copy all the files to your new PC, you used to have to use a crossover cable. If you didn't have an Ethernet switch hanging around, or anything, a hub to plug the 2 devices into, they wouldn't communicate. So if I wanted to plug 2 host machines, 2 PCs together, 2 switches together, 2 routers together, I would have to use an Ethernet crossover cable. This is not much of a problem anymore, because by about 15 years ago, the electronic component, the electronics chips have gotten so sophisticated. They have a feature called Auto MDIX, which means you can plug in a straight through cable or crossover cable, doesn't matter which one. The electronic circuitry will automatically sense the type, and he will use the transistors to connect the proper transmit wires and receive wires together. And you can use any cable type you want to. The third type of Cisco, the third type of cable for the Cisco CCNA, this is this baby blue rollover cable that plugs into the COM1 port on the back of your PC, and then plugs into the RJ45 console port of the Cisco router switch, because you need to plug into the console port to set up the device the first time. It has no configuration. You can't tell it up with a network to it yet. Doesn't have an IP address yet. It's factory reset. So this is a Cisco proprietary cable. It's called a rollover cable because the pin 1 of one end of the wire goes to pin 8 at the other end of the wire, and it's not twisted pair copper cable. It's what the phone company guys call silver satin cable. It's just flat cable. It has no noise rejection capability. You don't need that for a console connection because it's very slow speed. I think that Cisco made this on purpose so that you didn't accidentally try to use a rollover cable. If it wasn't rollover, it was straight through. You might try to plug 2 Ethernet devices together, and they would get a very poor Ethernet connection with lots of errors because there's no twisted pair cable. So I think Cisco deliberately rolled over the pin out so that you wouldn't accidentally try to use it and get a poor Ethernet connection, and then they'd call Cisco and complain about their equipment was faulty when it was the customer's wiring was faulty. So this is the type of cable that we use to plug into a Cisco device to set it up for the first time. Now, the issue is that these have this DB9 connector on one end to plug into the COM1 port on your PC. Most PCs don't have COM1 ports anymore. The old slow speed serial ports, they'll have USB ports now. So you can get from $10 or $15 from Amazon or other dealers, you can get a baby blue cable. It matches the color code exactly. And you can buy a cable that has the RJ45 connector that plugs into the console of your Cisco switch or router. And the other end has a standard type A USB port that plugs into your PC. You can even get the type C. You know, the old USB type A ports, you try to plug them in and it's the wrong way. You got to turn it around and get it to fit. The newer USB-C cables, sometimes called charging cables, they plug in either way. They're bidirectional. So there's a little chip in there that converts the USB circuitry to the old COM1, COM3 standard, and you can plug it into your Cisco device and set it up. So in our laboratory, we have the baby blue cables, whatever PC you set at, whatever desk you set at with your PC, you notice there's a baby blue cable that comes out and plugs in. Our computers actually have COM ports. And that plugs into, and that's your COM1 connection when you run TerraTerm and connect your first Cisco device up. Now let's talk about fiber optic cabling. Not as common as unshielded twisted pair cable because they are more expensive. Fiber optic materials are more expensive, but more importantly, the cost of the materials is a small part of the installation. The major part of any installation, regardless of whether it's copper or fiber optics, is the professional technicians and engineers that design and put the system in. You know, they got to bring out their ladders and move the ceiling panels and route all these cables every places and terminate them to the patch panels and get them connected. And fiber optic cable is more difficult to work with than regular shielded twisted pair cable. It's great for situations where it's too long for copper cable. So in all the classroom buildings we have on campus, there's a room in the center of the building somewhere where we use copper cabling between all the teachers and staff and student machines, plugs into that central wiring closet. At our classroom building, it's right outside our door. But if I need to go a longer distance, like from here to the library, from the business building to the library, that's much longer than 100 meters. And I can't just dig a hole in the dirt somewhere and put in a receiver and a transceiver in there to do that. That wouldn't be practical. So fiber optic cabling goes much longer distances and much higher bandwidth. It's much less attenuation because the pulses of light can go miles if we use the right type of cable. Completely immune to electromagnetic interference and radio frequency interference and crosstalk because there's no electricity. It's pulses of light. No worries about ground faults or other electrical faults like we have with copper cable. So instead of being made with little tiny strands of copper, it's made with tiny strands of glass. I call it a mirror tube. Shoot your light into one end of this mirror tube and it's going to come out the other end at the speed of light on the other end. And then we're going to use either a real semiconductor real ruby laser for really long distances, or a cheap semiconductor LED to emit the pulses of light that go into the fiber optic cable. Lasers, ruby lasers are several $100s. An LED semiconductor is like a dime. So that cheap Walkman CD player that you walk around with has an LED in it to read the CD and transmit it into the music. That's a very inexpensive component. So the fiber optic cable itself acts as a light guide, a wave guide, to guide the light between the two ends and have a certain small amount of signal loss that we're willing to live with. That it won't be, as we say in East Texas, it won't be petered out so much that we have to gussy it up and re-amplify the signals again. Okay, there are two types of fiber optic media. And the overwhelming trend these days is, it used to be single mode fiber was the more expensive and multi-mode fiber was the less expensive because it was more sloppily made. Technology has gotten better. If you're doing any type of new installation today, do not consider multi-mode fiber cable at all. Get single mode fiber. It's going to be the same cost as multi-mode fiber, and it's going to be high performance. Single mode fiber has a very narrow waveguide for the light. The light doesn't have the ability to bounce around and get distorted. Multi-mode fiber has a larger core, and the light as it goes in bounces around a lot, and so it can get some diffusion of the light, and it's not good for super long distance applications. So the rule of thumb used to be that we would run single mode fiber. Maybe the phone company or the internet service provider would run single mode fiber miles and miles and miles between facilities. And we use multi-mode fiber within a commercial office building environment. These days, though, throw out the multi-mode fiber. Just use single mode fiber for everything. So fiber optic cabling is used in enterprise-based networks where we want to connect devices together. We use it to connect our buildings together. on all our campuses. Each campus has got fiber optic between all the buildings on each individual campus. And then we have fiber optic connections to connect all the campuses together. Fiber to the home. Where you see these guys pushing pipe everywhere, now we have a lot of areas that offer fiber optic based, usually 1 gigabit type services from both the telephone company and the cable companies to give an internet service to home and maybe small businesses. Long haul networks are used by service providers to connect countries and cities together. This is usually the realm of the telephone companies and the big service providers. Submarine networks are the ones that go under the sea. So we used to use coaxial cables for that, but nowadays they've gone to fiber optic cables because that's more higher speeds and it's more reliable than the old copper-based coaxial cables. So at the CCNA, we're going to look at fiber within the enterprise. So if you're wiring up a network and you were, say it's something like, I'll tell you another story about in a previous life, I worked for this college publisher in downtown Fort Worth, and we had 80,000 square feet, and some of us were on the 26th floor, and then we also had floor 32 and 36 and 37 and 38. Excuse me. Now the distance for copper cable is about 328 feet. 100 meters is about 328 feet, about the same as the distance between the goalposts of a football field. So when we connected all these, I was engineering our Novo network, and we were going to connect all 250 people that worked in our 8,000 square feet together so they could share printers and share files. And it turns out that in a big office building, the distance between the 26th floor and the 38th floor is a little bit more than 328 feet. So I said, we must run fiber optic cable between all these floors to our data center, which is up on the 30th floor. And the same thing happened when I asked for the Category 5 copper cabling. They said, no, that's too expensive. We're not going to do that. We're going to run your Category 3 cable down there. Well, I had to work with it, and it turns out that if you're slightly more than 328 feet at standard 10 megabit speeds, you can get away with it. Not much more. It was only about 10% higher than that level. Should have used fiber, but when you go and get a job in the computer business, check out the company you're going to work for. Here's the way to tell whether it's going to be a good company or a bad company. If the IT guy reports to the chief financial officer, that's bad. Chief financial officers have great math skills, and they're good with budgets, and they regard each and every expense as something to be reduced. I reported to the chief financial officer. He didn't want to approve these things. Try to work for a company where you report to the chief technology officer. In a company that has a separate chief technology officer, who is a peer with the chief financial officer and the chief executive officer, the chief technology officer has a way of presenting IT issues as something that brings value to the company. I really think it shouldn't be called the IT department. I think it should be called the Technology Value Center. The chief technology officer knows how to bring value to the company and increase the profits by appropriate use of IT technology. So if I reported to the IT chief technology officer, he would say, oh yes, we're going to get better bandwidth and future-proof us if we use this fiber optic cable. Of course I will approve that. Okay, end of story. Rant mode off. So we're going to use fiber within the enterprise in this. Okay, so sorry, microphone muting issue there. So the straight tip connectors and the subscriber connectors, you can plug them in incorrectly, and the transmit and the receive might be incorrectly wired. The connectors on the right, the LC connectors, they're like an RJ45 connector. It's impossible to plug an RJ45 connector in incorrectly. And with those type of connectors on the right, the LCs, you can only plug the fiber optic cables in correctly. With the SC connectors and the SD connectors on the left, it's possible to plug them in incorrectly. Transmit to transmit, receive to receive. And you gotta, if they don't work, you gotta just unplug them and plug them in the other way. So future proofing or idiot proofing, I like the ones on the right. Patch cords are like RJ45 patch cables for Ethernet, except they plug in fiber optic transceivers from one end to the other end. So they sort of have the same physical appearance. Which one of these would you rather plug into, and you can accidentally mess it up? So this one, this one, this one, you can plug them in backwards. This one is a better choice because it's impossible to plug it in incorrectly, just like it's impossible to plug in an RJ45 connector incorrectly. So let's compare copper, unshielded twisted pair copper with fiber optic cabling. Unshielded twisted pair cable is good for about 10 megabit, the old standard Ethernet, to about maybe 10 gigabit, depending on what categories. Category 3 cabling, no, that's going to support gigabit. But category 6, category 7 cabling, yeah, that's going to support 10 gigabit for relatively short distances. Unshielded twisted pair cable has a low immunity to electromagnetic interference and radio frequency interference because it's copper cabling with electricity running through it. So we have crosstalk and we have electrofrequency interference. We've got to twist the wires together, maybe shield them. Low immunity to electrical hazards. So ground faults could actually induce a personnel hazard on the wire because they could shock the personnel. However, it wins very much in cost of the materials. Installation skills required are kind of a lower tier, and we don't have to worry too much about safety precautions because it's usually low voltage wire. Now, looking at fiber optic cabling, it's capable of incredible amounts of bandwidth. We keep discovering higher and higher amounts of speed that fiber optic cable can go to, and we can go very, very long distances, miles and miles and miles. And the great thing about fiber optic cable, besides the super long distances and the super high bandwidths, are it's completely immune to electrical problems. It's not electricity, it's pulses of light. It's not affected by electromagnetic interference or radio frequency interference. However, it costs most, requires very high installation skills, and safety precautions, it's lasers. What's the rule that the laser guys use? Do not look into a lit up fiber optic cable with your one remaining good eye. Well, yeah, it can blind you. So, you know, they use tricks like shining it on a index card or looking at it with the phone on your cell phone to look at it. Don't look at it with your eye. It can actually cause blindness. Okay, wireless media such as Wi-Fi. Instead of using pulses of light through a fiber optic cable or electrical energy through a copper cable, we're going to use radio frequency energy. So this has some limitations because the coverage area, our Wi-Fi devices are very low power radio transmitters. They're not allowed to use a whole bunch of electricity, a whole bunch of power, because there'd be other people in the next block that would be overwhelmed by it. So the coverage area is limited to something 300, 600 feet, something like this. Wi-Fi is a shared service with other services. For example, Wi-Fi and Bluetooth use the exact same frequencies. And coincidentally, the exact same frequency is used by baby monitors and microwave ovens. Oh my, and some cordless phones too. So different devices can interfere with you. And according to normal FCC rules, if you're experiencing interference, you're told to stop using it. We're not going to shut the other guy down because he's an approved emission as well. It's radio frequency waves that anybody can hear. So take your laptop to a Starbucks, put a copy of Wireshark on it, and you can see all the data that everybody else in the coffee shop is using. So anybody can gain access to that information. If you don't take care and use security and encrypt your data, anybody can see your data. Now, Wi-Fi's operate in a half duplex mode, which is like the old Ethernet hubs. Only one thing can transmit at the same time. We get collisions. So that means everybody has to share the same bandwidth. Now, some newer Wi-Fi's, in their defense, some newer Wi-Fi's use multiple antennas like MIMO and multiple transmitters, and it's more like an Ethernet switch than an Ethernet hub. And you can get more bandwidth for each user. Okay, here's the types of Wi-Fi wireless media. So we have the 802.11, the standard for wireless Wi-Fi. Wi-Fi started shipping around 1999, 2000. They started putting the old 802.1b, 802.11b standard in consumer machines. That was the old fairly slow bandwidth. There's a Bluetooth standard, 802.15, which is intended for a wireless keyboard or a mouse or an earphone with a cell phone, something of that nature. Not supposed to be super long distances. Let me tell you this, what I heard. The hackers have a convention in Las Vegas every year, and they teach each other about their new hacking methods. And they took some Pringles can antennas out in the desert outside of Las Vegas, and with both Wi-Fi and Bluetooth, which is the same frequency, they got 50 miles. So don't assume that just because you're using a Bluetooth keyboard that nobody else can hear it, they might be able to tap into it. A WiMAX is you're going to build a tower somewhere, like on the west end of Galveston Island, where there's nothing but mosquitoes and rattlesnakes, and you want to give internet service to the people that have cabins out there, vacation cabins, where they come out and stay for a week. So WiMAX 802.16 is this transmission tower, and it's kind of similar to Wi-Fi on steroids. You can transmit it to all these vacation cabins, and they can pay you $9.95 a day or something, and they can get internet access while they're on vacation. And then Zigbee, IEEE 802.15.4, is a very low data rate and low power consumption for Internet of Things applications. Think of things like electrical power meters, parking meters, things of this nature. That this Internet of Things, whole Internet of Things scheme is that I can drive to the concert in downtown Fort Worth, and the Internet of Things will tell me where's the best place to park, where there's a parking meter that's not being used right now. So wireless LANs require a wireless access point. At home, your wireless access point is your home router. The cable companies and the telephone companies are both giving, typically we would have a home router, and then we would have the cable modem. Or we have the home router and the DSL modem. And the current trend is for the cable companies and the phone companies to give out an integrated device. It's a cable modem and a home router all in one box, complete with Wi-Fi. I got that from the phone company. I've got one box, and it's like a PBX system for my landlines. It's a Wi-Fi for my Wi-Fi devices, and it's got the 4 Ethernet jacks for my wired devices. In a business, that's the thing that's up in the ceiling of the room, so that when you come into the classroom with your tablet or your phone and you need Wi-Fi access, you can connect to the existing network. And then we need a wireless NIC adapter in each individual host device. So your telephone has got a wireless NIC adapter. Your tablet, your laptop PC, it's got a wireless NIC adapter in it. Now he has a mention here that network administrators, that's going to be you guys after you finish this course, network administrators, technicians, and engineers must come up with some means of having security policies to protect wireless networks from unauthorized access and damage. Now, at Tarrant County College, you're not allowed to plug anything you have into our existing wired Ethernet. We give you free Wi-Fi, but you're not allowed to plug your device that you own into our wired network because you're probably full of viruses or something. You can use our free Wi-Fi all you want to. Now, our Wi-Fi is not encrypted. There is no security whatsoever. There's no encryption standard that you have to attach to. So therefore, anybody can see. We're providing it as a convenience to all the students and the public. They may come in and use our free library. They can have free connection to the internet from this. Now, if you want to set up a VPN when you get there, you can have protection and do that yourself. So our wired network has very stringent security. You can't attach any device to that. It's going to get scanned and partitioned off the network because it's not recognized as an official Tarrant County College device. Okay, hang loose and I will go to the next numbering system. Okay, dreadfully boring number systems. Here we go. This is about as exciting as the dreaded, feared, and hated OSI 7-layer model. We're going to look at binary numbers, and we'll look at the hexadecimal number system. Now, of course, computers use binary numbers. They use binary number systems. They use ones and zeros, like transistors being on and off, to represent zeros and ones in the computer RAM and operating system and the CPU. Everything is going to be reduced to ones and zeros, no matter whether it's a JPEG file or a data file or operating system or whatever. So in IP version 4, which is our legacy version of network addresses, when the engineers and the architects came up with this scheme, they made the wise decision that, gosh, if we require all our non-technical users to key in 32-bit IP addresses, they're going to go nuts. They're going to look at all those ones and zeros. I'm getting a headache just looking at them. I can't compare those numbers to each other and see if they're the same number or a different number. It's too difficult to see this. I've been using the decimal number system since first grade math. Why should I have to look at the binary number system? So the architects and engineers that came up with the original IP numbering system said, we'll use something called dotted decimal. For ease of use by our non-technical users, we'll just have them look at network numbers like 192.168.1.1. So the binary number system represents these bits levels with ones and zeros. In the decimal number system, we have the digits 0 and 1 through 9. So every device that's on the network uses a unique binary address for its unique identity and to identify the other devices. We're going to take these 32 binary bits and divide it into 4 sections, octets. Each octet is 8 bits, and each 8 bits is the dotted decimal number. So you key in the 192.168. Look at the diagram on the left here. Let me see. So, oh, look at all these binary numbers. Oh, that's incomprehensible to me. Oh, this is easier. 192.168.10.10. 192.168.11.10. I can easily look at those numbers, compare them, and see that they're different valid numbers. So this is the system that we used. And even our idiot user, I'm sorry, that's not nice. Even our untechnical users don't have to worry about the dotted decimal stuff because they'll be using domain names like PC1, PC2, company.com, and so forth. So in the decimal number system, we have our positional value, which are powers of 10. 1, 10, 100, and 1,000. So if I have the decimal number 1, 2, 3, 4, that literally means 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4 times 1, and that gives us our 1,234. In the binary number system, we're going to use powers of 2 instead of powers of 10. So in the binary number system, instead of using powers of 10, 10 to the power 0, 10 to the power 1, 10 to the power 2, we're going to use the binary numbers. The binary values the base 2 number system. So we have 2 to the power 0. And by the way, any number to the power 0 is 1, except 0. Any number to the power 1 is that number itself. 2 squared is 4, 2 to the power 3 is 8, and so forth. So we get our place order values here: 1, 2, 4, 8, 16, 32, 64, 128. So we have 8 binary numbers. The very highest number you can have is the sum of all of these numbers. So 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 is 255. Have you seen that number before? Oh yeah, 255.255.255.0. That's the biggest number you can have in a dotted decimal number. If it's bigger than 255, it's invalid. It's bogus. So that 192.168, let's take that 192 number. In binary, it's 128 plus 64. Adds up to 192. So if you can look at the bits of code representing that 192, it's 2 ones and 6 zeros. So let's convert binary to decimal. We'll just take those binary numbers, and everywhere that placeholder value is, in this case, let's take the the binary number, this one right here, 10101000. To convert that number to decimal, we're going to take the placeholder value of 128, no 64, 64 is 0. We're going to add 32, we're not going to add 16. We're going to add 1, and we're not going to add any of these last numbers. And we come up with the summing of these values together, we get the number, we get the sum of that number, and it converts it to 168. So 192.168.11.10 is represented by all these binary bits. Internal to the computer is all ones and zeros. He just has a binary line. So everything that we use a computer for, we're going to see the decimal numbers on the screen when we run Excel. We're going to see the JPEGs and the MP4s when we look at the graphics. But it's all going to be ultimately converted into ones and zeros, so it can be transmitted out the wire to other devices. Now, decimal to binary conversion, we're going to take the number and how big is it? So we're going to take the number and say, is it bigger, equal to, or bigger than 128? If so, I'm going to set the 1 bit for 128. Then I'll subtract 128 from that original value if it was bigger than 128. And then I'll do the same thing with the 64 and the 32 and the 16 and subtract these out until we get to the binary equivalent of that number. This is the easiest method for converting between decimal and binary. There's another weird method where you divide and take the remainders, but I think this method is easier. So let's take the example of a number 168. What is the binary equivalent of 168? Well, is 168 bigger than 128? Yes, it is. 168 is bigger than 128. So let's put the 1 here. Okay, we got our 1 there. Now let's subtract 128 from the 168, and our difference is 40. Now let's take a look at our 40. Is 40 bigger than 64? No, it's not. We don't put a 1 in 64. We leave it to 0. Now, we don't have to subtract anything. Is 40 bigger than 32? Well, it is. Let's put a 1 to account for that 32. Subtract the 32 from the 40, gives us 8. Is 8 bigger than 16? It is not. We do not put a 1 there. We leave it at 0. Now, 8 is equal to 8, so we put a 1 there. 8 minus 8 is 0, so all the remaining bits are 0. So that turns decimal 168 into this 1, 0, 1, 0, 1, 0, 0, 0 pattern. Now, in the Windows operating system, there's a thing called the calculator. And if you bring up that calculator in Windows and click the programmer mode, you will see that he can convert back and forth between decimal and binary and hexadecimal. You can use that to check your work. So we have this concept that routers, computers, computer-like devices only understand binary numbers. Humans work in decimal. So we have to see how they work together with each other. Scary, but we have to know it. Now let's look at hexadecimal. Hexadecimal is used for really, really large numbers. IP version 4, we used to only use binary and decimal, dotted decimal. But MAC addresses, the physical burn-in addresses of Ethernet devices, are 48 bits. The old Novell network was 64 bits. The new IP version 6 is 128 bits. So we're going to use the hexadecimal number system, which is base 16 instead of base 10 or base 2. Now the problem is, in the decimal number system, we have 0, 1 through 9, but we need a single character to represent 10, 11, 12, 13, 14, 15 are 2-digit values in decimal. We need a 1-digit character to represent these values 10 through 15. So we standardize on the letters A, B, C, D, and F. So typically when you look, if you run the command ipconfig/all on your desktop PC to learn what the MAC address of your PC is, you're typically going to see some A, B, C, D, E's, and F's in there. If you see them in there, you can be pretty sure it's a hexadecimal value. Hexadecimal maps exactly to binary because each hexadecimal bit, for example, the hexadecimal bit E, hexadecimal value E, is exactly equal to this binary pattern. So it's very easy to convert back and forth from hexadecimal to binary using this chart. So in IP version 6, there are 128 bits. Now that's too many to write out ones and zeros. It's really too big to use dotted decimal for. So we're going to take this 128 bits and divide it into 8 16-bit pieces, and each 16-bit piece, using our base 16 hexadecimal number system, will be represented by one character. So we can write out an IPv6 address by using the hexadecimal characters. We're going to call those, instead of octets, we'll call them hextets. To convert decimal to hexadecimal, we're going to use the procedure where we convert the decimal number to 8-bit binary strings. We already talked about decimal to binary. Then take each one of those binary strings and convert each 16-bit group of binary strings into the hexadecimal equivalent for it. Fortunately, we have our charts to help us with. Hexadecimal to decimal, we're going to take that hexadecimal number, 0, 1 through 9, A, B, C, D, E, F, and convert it into the 4-bit binary strings, and then convert that into the decimal digit. Again, this is a great feature where your Windows scientific mode or programmer mode calculator can help you in doing this to understand how it works. I think that's it. Is that it? Okay. Well, all right, I'm going to hang loose for 1 second in case there's any chat inquiries, and then we'll call it a day. And hold on, let me stop recording.